All right, this is advanced Postgres schema design for scalable application development. My name is Serap Sarkouni. I'm the founder of a company called JackDB. Hey there. It's a database security product that allows access to a lot of different databases, not just Postgres, but it provides a uniform environment to access all your databases straight from your browser and provides auditing and access controls. I'm also a maintainer of the JDBC project, the Java driver, one of the maintainers. And I also contribute to the Node.js driver, Node Postgres. So this talk is about schemas, particularly like advanced features you can use in Postgres to make smarter schemas and better schemas. These are two of my favorite quotes when it comes to just overall design of data structures, because at its heart, schemas are the design of how you're structuring the data within your database. I'm not going to read the quotes, but these are kind of like what I think are really, really smart quotes on just the importance of data structures versus code itself. Because the gist of it is when the data structures are sound and apply directly to the things you're trying to do, the code itself becomes very straightforward. Kind of summarizing things with this other smart guy that I know is that dumb schemas require really smart code. And if you have smart schemas, they stop dumb code. And by dumb code, I mean people doing things that they didn't think that they were doing, but they end up happening anyway. So when you look at a database, what's unique about a database versus other pieces of software is that there's lots of applications interacting with a database. It's not just the one app that's talking to it, because a database by its nature is a concurrent system. So you can have a reporting system talking to the database. You can have an OLTP system that's actually modifying the data that's there. You could have a new version of that OLTP system that maybe is working, it's supposed to work the same way, but you don't really know for sure because it's running different code. And at the end of the day, the schema of that database is like the API for that database. It dictates all the things you can do, and it also dictates the things that you can't do. So, the schema might, the distinction between these two things is that, a schema empowers you to say that here are the things that you can access. These are the things that you can write. This is how you may write them. You have, the permissions, you have procedures and functions that you might be able to execute. And all these things are things that it enables you to do. So whatever tables are in a schema, whatever views are in a schema, if you have the proper permissions, you can query them. And, possibly insert into them and modify them. But even that, being able to do something doesn't mean it's necessarily something that is feasible in the real world. So as an example, if I have a table with like 1 billion rows inside of it, if I have select rights to that table, like in theory, I have an application that could do anything with that data. But in practice, reading every single row inside of that table is going to be completely useless because, if I'm making like a web app, for example, I'm not going to have it spend 6 hours processing a web request. So the performance ends up being not just something that's, it's not just a user experience thing. The performance is actually changes things from being possible to just being completely impossible because it's just not reasonable to expect someone to wait 6 hours for a result. So it's not just you can do something technically, it's can you do something within the confines of actually getting it done in a reasonable amount of time. Now, on the other side, there's things you can't do. And by things I can't do, I mean things you shouldn't do. So, if you have data you're not supposed to put in a particular table, or like, having balances be negative, or having the relationship between things actually exist. So these are, I'm sure all of you have heard about foreign keys and check constraints, things like that. The whole point of the can't do aspect of a schema is to prevent you from doing things that you just don't want to happen. You have certain invariants about your database, about your data itself that you want to maintain. And you want these things to be maintained regardless of who is accessing this data. So when you're changing that data, I don't care if it's program A, program B, some program I haven't even written yet, I want these invariants to always hold because when I'm querying this data afterwards to present it, to read it, to transform it, I want to be able to rely on these things to be true. Your balance should never be negative. Whenever I have a product, there should also be a sale ID associated with it, whatever these relationships are. So when it comes to defining a schema, you have different priorities. There's the priority of how fast is it going to be to use, how simple is it to do, how many pieces are there involved in it. But the number one thing is consistency. The number one thing you care about when you're talking about data is you don't want to lose your data, but you also want to make sure that the data that you're storing actually, relative to itself, it makes sense. So the priority order for designing any schema, the number one thing is always consistency. It has to be, what goes into your database, that your schema should remain consistent. After that, you have efficiency because, whatever's inside of there, I want to be able to access it as efficiently as possible. And if I can't access something efficiently enough, if it's too slow to, like, my billion row example of querying something, to get a total, let's say, for a table, it's just totally impractical to be able to access it anyway, so it ends up being not usable. And then the third one is you want simplicity, and the reason you want simplicity is because when things are complex, they tend to break, they have weird edge cases, people tend not to understand them, ramping up people to work on them becomes complicated. So you want things to be simple, but it's not the most important thing. The most important thing is what? You want to prevent bad things from happening. Then you want to be able to import, and that's more important than empowering the good things that you want to do. Making sure that the data itself is correct is more important than making sure it's fast. And making sure it's fast is much more important than making sure it's simple. So if you have to pick, this is kind of like the pecking order of every time you're going through and designing anything. Now, when you're designing a schema, the core parts of a database, in a database schema, at the bottom you have columns. Those columns are listed together in tables and views. A table and view has a bunch of columns. Those tables themselves will have relationships to other tables, so you have foreign keys between them. And then you have permissions, which are outline who can actually access what. So there's some mishmash of listing of access between these things. But you can actually go one level lower, and that's the data types for the columns themselves. And that's where the real design of a schema starts. Because each of those columns has some kind of type associated with it, because Postgres is an actual, it's a strongly typed database. And Postgres is actually one of the greatest strongly typed databases ever, because it has a lot of data types. Like, it has more data types than you can imagine. You can make your own data types. And there's like highly specific data types. So, if I have an integer, I can say how big it's going to be. It's going to be 2-byte integer, 4-byte integer, or 8-byte integer. You have date types, timestamps. There's, besides just text itself, there's other text-like types for characters. We have specific types for like UIDs. My personal favorite is actually Boolean. Like a database, like there's many database systems that do not have a Boolean type, and it's actually really annoying because you never know for sure, is the guy going to, are they going to put a 1 and a 0, or are they going to put a T and an F? It's kind of ambiguous. Whereas in Postgres, there's a defined type for it, which makes it very clean. Which also lets you use that Boolean type inside of SQL itself. So you can just say like, where is active, and it reads more legibly. So yeah, there's many more complicated types, intervals, ranges, all this stuff, and then you can kind of combine together and make your own. Now, for all these, anytime you're working with data types, the first thing you have to think about is the size of the data type. So if you look at these two fish here, if you look at these two fish, which one would you think is the happier fish? It's like clearly it's the one, he's in this, this little fish in like the big bowl, he has more room to swim around. But as like someone designing a schema, you have to look at that fish bowl and say, oh, I can fit so many more fish on that other side. Because you have this tiny fish there, and like, similar with these data types, the smaller the data type is and the more compact the representation is, the more you're going to be able to fit into memory, the more you're going to be able to fit into disk, and the smaller your indexes are going to be. So one of the probably best and worst examples of this, depending on how you look at it, is UUIDs. So coming from a lot of other systems, like other, let's say, not so great database systems that don't have a defined UUID type, people tend to use text for UUIDs. So that can vary from, actually just having the bytes themselves as like hex in there, or actually having the, the full thing with the dashes, which is the most common one. And you can do that in Postgres as well, because I can just define a text type and I can put it in there. If you do that though, that's the top example here where it's defined as text versus the bottom example where I'm using the actual data type for UUID. It is significantly bigger. And the reason for that is the UUID represented as text is going to be that, it's 36 characters with the dashes inside, whereas the raw bytes themselves are 32 characters. Or 16 bytes. So you're looking at 32 characters plus 1 for the length, just because of the way that Postgres stores varying length data, versus just 16 bytes. And this would cascade to everywhere you're using it. All your indexes are going to be bigger. All your, every field that's using there is going to be bigger. Every leaf level of the index, the branch level is going to be bigger too. So having this be the actual type makes it significantly smaller. It's faster, but there's actually something else that's even more important than it being smaller and faster. And that's that it's correct. Because if it's just a text type, unless you go out of your way to add additional constraints on top of it, you're going to be able to insert anything into that text type. Whereas if it's a UUID, Postgres knows it's a UUID. It has to be 16 bytes. I mean, Postgres doesn't actually check because there's different types of UUIDs. There's like type like V4, V3, V whatever it is. So you can put like anything that's 16 bytes inside of there, and it'll kind of assume that there is a UUID that matches that type. But you can't just put arbitrary text inside of there. And each one has a single, there's one representation of it, which is the raw bytes. There's no concept of like uppercase characters, lowercase characters, and things like that. Whereas if you're storing the text one, you have to be consistent. If I store it as lowercase, then I have to query it as lowercase and vice versa. So it's not just faster, it's actually more correct, and it stops you from doing dumb things like inserting the wrong thing into your ID field. Now, when it comes to actually laying out your columns inside of a table, the order that you put them actually makes a difference. So if anyone has experience with like C programming, when you lay out the fields inside of a struct, each field has to be aligned based on the size of that field. So as an example, if you have like a 4-byte integer, a 4-byte integer can't just be at any random place inside of memory if you're going to treat it as an actual 4-byte integer. Inside of memory, when you have a C structure, it makes sure to allocate it only at like a 4-byte modulo 4 memory location. A 2-byte integer has to be at 2 bytes, an 8-byte double or an 8-byte 64-bit integer has to be at 8 bytes. Internally within Postgres, it's the same thing because the disk format for Postgres is designed so that you can have the pages, when they're loaded into memory, you can just read things from the pages. So if there's an integer somewhere, you can dereference that and read it as an integer. So the date alignment, what ends up happening with this is that since a field has to be aligned based on the size of that field, my example on the left here where first I have this Boolean, which in Postgres is represented as 1 byte. Then I have a big int, which is Postgres, it's represented as 8 bytes. It's a 64-bit integer. That 64-bit integer cannot actually fit right next to the Boolean. I have to align it at 8 bytes. I'm at the first byte. I have to skip the next 7, and then I can put the big int afterwards. Okay, I do that, and then I'm going to have another Boolean after another big int. And what ends up happening is it's pushing the thing out further and further. So this ends up being that you have significantly more size for this row, even though it's the exact same data. Because when it comes to the table, the order of the fields themselves don't matter. You're still like, I can query these in any order, A, B, C, D, whatever it is, and how it's stored is almost like just like a bag of stuff. I'm pulling out the fields out of that row. So what's actually happening is the first one, that bad example you're seeing here, the first byte over here is that Boolean, and then there's 7 bytes where it's just completely empty because it can't be used for anything, and then the next double starts. So those 8 Ds afterwards is the next is the double. And then you have another Boolean and another 7 bytes that are empty. Another Boolean, another 7 bytes that are empty. So what's interesting about this is, one, by just sorting this by biggest to smallest, by having my biggest fields come first, and then and then my medium fields and my small fields, you naturally get the optimal solution for this. But you can also get there a couple of different ways if you know the specific sizes. Like if I know I have 2 Booleans, I can put like a 2-byte, like an int2 next to it, for example, and it'll align correctly. But also, if you just think from bigs to smalls, you never have to think about this because it just naturally sorts. What's also interesting is if you look at that second example where I have the double, 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 and then Boolean, 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 I can add 5 more Booleans to that without increasing the size of the row. Because the entire structure itself has to be aligned at least to the size of the largest element within it. So since I have a double inside of there, the doubles themselves for the next row, if it's going to sit next to it, has to be aligned at the 8-byte boundary. So what that ends up happening is that you have this extra space there that you can put something in. So if I added a new column, it wouldn't actually add new space if that column is smaller than is small enough to fit in that piece on the end. So as a general rule, if you just go from biggest to smallest, everything will be as small as possible for your structures. So we kind of saw an example of this already where if you have something that's not just text, if it has another representation, you should use something else for it because text is for text. Postgres has one of the most fantastic text types. It automatically handles compression through toasting. You can put anything up to, I think it's like a gigabyte or something inside of there for the text itself. It handles all kinds of encodings. But you really shouldn't use it for anything besides text because that's what text is for. For UUIDs, clearly you should use a UUID type. It has, it's optimized for that. For a lot of these other ones, by having a number, you ensure that the data inside there actually is a number. For dates and timestamps, again, there's more specific types. And even for binary data, you end up just doubling the size of your data. So if I'm going to store my binary data as hex inside the database in a text field, it's going to be twice as big. If I'm going to store it as base 64, it's going to be, 5 over 4 times as big, the size of the thing. So everything, you're just paying for this extra size for no reason, and you're losing the type checking along the way. So just don't use it. So check constraints. Check constraints are kind of like the building block of validation within your schema, of defining these invariants at the column level that you want your data to hold. So in this example, we have a person table, and we have these two check constraints on there, one on the username and one on the name itself. And Postgres, it has a lot of great features, one of them being these regular expression conditions over here. So here I'm saying that the username has a regular expression, wildcard regular expression. Actually, that shouldn't be a wildcard. That should not be a wildcard. Matching this regex over here. So what this is saying that this username has to match this regex, and they'll be checked for every value that's inserted. So what this means is that I never have to worry about reading some username from this table that's not going to match this regex. And I never have to worry about if I insert something into this table, it will not let me do it. It will give me an error, and it'll actually give me a very specific error if I try to do it. Similarly, for like the name field, there's a check constraint on the length of the name. I don't want it to be more than 255 characters. So these are things you can actually change afterwards too. You're not set in stone for the check constraints, because modifying them, there's like blocks and stuff involved for validating the data, but it's not set in stone as far as like changing the data type itself would be. But what it does do is it allows you to define those invariants, and you get to stick with them afterwards. And by defining these things with what I could call descriptive names for the constraints themselves, it opens it up so that on the application side, you end up being able to know exactly what went wrong. So if I try to insert something and I see that it violates check constraint person check username pattern, it's immediately obvious what is wrong here. Oh, my username is bad. So I've seen a lot of like ORM-driven, like I think Hibernate's like the worst offender for this, where ORM-driven like schemas, where they'll define like foreign keys, check constraints, things like that, where it's like FK and then a whole bunch of like numbers afterwards, or like CK and then some UUID or something defining, because they just want some unique value. But it loses the developer focus for it, because now when the guy sees you inserted some data, you're trying something out, and you just see like CK 1 2 3 4 5 6 failed. You have no clue what it is. Your code, if you actually do try to catch it, is going to look really weird. So if you actually go out of your way to define these things correctly, it pays dividends afterwards, because you have this clear description of what's going wrong inside of these things. So that same concept of check constraints can be extended out now beyond one field. So if you have multiple columns, you can start defining relationships between these columns, but on the same row that that must hold. And again, these you can define invariants like in this example, I want to ensure that there's only one manager associated with a widget. That manager could be a person, that manager could be a group, but there can only be one. And the way you do that is by, again, defining this check constraint, saying that one of these fields has to be null. If one of these fields is null, it shouldn't be the same as the other field being null. There's a lot of ways of writing these kind of things. If you study like Boolean algebra, there's a lot of ways of writing this. So it's really just picking whichever one you think makes sense when you're for you reading it back again. But again, the idea here is you have a constraint, you have some kind of descriptive name for it, for that invariant you want to hold. And Postgres will make sure that this happens, and you never have to worry about reading anything, having the system be in any state where this is not true. So Postgres has a concept of arrays, and it has arrays of really any data type. So whatever data type you have inside of Postgres, there's also an array type associated with it. And arrays are very interesting, let's say, as a data type, because you can do some really cool stuff with them. A lot of the time when people use them, it's not really a good idea, though. If your default instinct should not be to, hey, I can put this inside of an array, because you probably want individual rows for what you're doing, and you really have to think through while you're actually storing an array for something. But there are times when it is incredibly useful. Like you actually do have like a series of things that like you want as one set that is tied to a specific row. You're not going to have multiple rows for it. I want to be able to like update that as one thing together. I don't really use arrays that much when I'm designing schemas in the fields themselves. I use them a lot in queries, because it's a great way if you're passing in, if you want to pass multiple values into something, Postgres lets you have a parameter defined as an array, and then rather than having like 10 parameters for something like an in expression, I can say like equals any, and then it'll say any of the values inside this array. So arrays have a lot of gotchas. If you're using it for somewhere where you're actually storing the data, not just like a one-off within a query. Some of the biggest ones are arrays in Postgres have no concept of like restricting the dimensions. Any array in Postgres, the type itself can have any level of depth of the array. So the example you're seeing here, this is like a text array, but under the covers it's actually two-dimensional. So the first dimension itself is like an array with two fields, and then the second level underneath is you have foo bar as like an array, and then baz bam as like another array. So if you just define like a text array in Postgres, or really any array type, if you don't go out of your way to restrict it further of what you're doing with it, in theory you can insert anything into there at any level of dimensions is acceptable data for that, just because of how arrays work in Postgres. There aren't different types depending on the dimensions of the array. There's just one type, and it's up to you to to kind of know what you're doing with it. And then there's other issues with like duplicates and ordering, just because by definition arrays don't have either of those. Now, if you are going to use arrays for something like this, it's a good idea to know exactly what you're putting in there. So if you have an array of stuff, more than likely your array does have a fixed dimensions. So here's an example of kind of adding some more checks we can do on top of arrays to tighten what's allowed to go in there. So the first thing we're doing here is we're defining like a generic function called array sort, which takes any array. Postgres has this concept where you can have functions defined without a specific type. You can say any is the type, or any array as saying it has to be an array, but it could be an array of any type. And it'll kind of infer at runtime what it's going to do with this specific data that gets passed in. So this function array sort takes any array and returns you back that same array sorted. And if you look at it, it's one line. It just says unnest the array and then sort it and then aggregate it again using array ag. Now, what's cool about this function is it's an immutable function, which means that anything I pass in there is guaranteed to give you the same result afterwards. It's not dependent on any third-party state, the state of the database, or anything like that, which means I can use it inside of things like constraints. So if you're looking here, I have two constraints on this table foo on my array. The first one is saying that the number of dimensions of the array has to be exactly one. So that means I can't have an array with 2 dimensions or 3 dimensions or 4 dimensions. So like this example over here with my two-dimensional text array would not be acceptable here. And the other thing I'm doing here is saying that the array order, like my array has to equal the sorted version of itself. And what Postgres does there means that every time I'm inserting, updating, or updating this field, it'll make sure that these invariants hold. So someone reading this could, they could actually rely on the fact that the array itself is sorted and it's one-dimensional. Because again, you can't, if you have multiple systems interacting with a database, you cannot guarantee that one of them is not going to screw up and insert something it's not supposed to. You could extend this further if you wanted to, if you want to prevent duplicates, for example. You could have another function like array unique, let's say, which is to select distinct array, like array ag of distinct, and it will return back the distinct elements of the array again as an array. And you could put another check saying that the array has to equal the same array unique, and that would ensure that our array is single dimensional, in order, and it's unique, which is probably a good thing for inserting data because you deal it once on the way in, and then everyone else can just rely on it afterwards. So outside of like let's say normal data types that describe a schema, like describe columns inside a schema, you have things called flex fields. So anyone who's worked on kind of like older systems at big faceless corporations that don't like changing things has probably dealt with flex fields. So flex fields happen when people don't want to change their database. So you'll have like a system, they're defining like an account table or a user table or a widget table, whatever it is, and they just don't want to change the database afterwards, but they don't really know what they're going to be doing next week, next month, next year. And they still want to be able to put stuff in there afterwards. So like, a long time ago, these guys came out with this genius idea. We'll just add like a whole bunch of fields at the end of every table called flex 1, flex 2, flex 3, pick like 10 fields, 20 fields, whatever, some insane number of text fields. And every time we need to use a new field, we have we can just pick the next flex field. And again, the number one reason for this is just people don't want to do database migrations. Or they work in some kind of organization where doing database migrations involves like some inordinate level of bureaucracy. Not so much this is kind of like more of an older problem because people have kind of walked away from this, but you still do see it, and you really don't need it because like rather than like avoiding avoiding migration, you have to kind of just embrace it. Because there's 3 kinds of databases. There's the ones that change, there's the ones that are never going to change again, like you have some static system that you exported, and they're the ones that don't exist anymore. The last one, if you drop the database, you really don't care about migrations, obviously. If it's read-only, you probably don't care about migrations because by definition, if it's read-only, you're just not going to touch that system anymore. You have some archival system you want to just be able to query. Everything else has evolving schemas. If your application code will change, at some point you will require either saving something new, changing the way you save something, changing the way things are indexed, like something changes. And good schema design is, it's not just having a bunch of flex fields, it's embracing that change through migrations. So there's lots and lots of tools for schema migrations. Everything from just having a bunch of SQL files to, there's Skitch, there's, I think just about every ORM has its own concept of like schema migrations. It doesn't really matter which one you use. I mean, you have to pick something, obviously. So whatever works in your environment, works with your tooling is probably the best choice. I personally just love individual SQL files. There's a lot of different migration tools that work with individual SQL files. So you're not really tied into like one thing. And Postgres, just by its nature of having transactional DDL, makes it really easy to have individual SQL files. Because you end up having these like, just individual chunks of do this, do this, do this in one transactional state, like one transactional chunk, and you can guarantee consistency along the way of the things you're working on. So when it comes to schema migrations, if you're coming from like a source code world of like a developer, let's say you're working with like Git, for example, when you're working on code, there's two ways you can go back in time when you're working on code. You can either, do like what's called like a reset. So you can say like reset, give like the hash or the tag of like a different branch, and like it'll reset your current work to that point. Or you can do a revert, which will actually create a new commit that backs out whatever you tried to revert. When it comes to databases, by their nature, they only work in one direction. They only go forward. There's no concept of like, really reverting a database. I mean, you can restore a backup to before it was. I mean, in theory, that's restoring it. But you're going to lose everything else that happened along the way. So if you had like a bad migration, something didn't make sense, we shouldn't have added this index or something, you're not really going back to before you had it. What you're doing is you're going forward to a new state where it just doesn't exist anymore, where you're dropping that object you did, or you're backing out the changes by an explicit state forward. So that picture's a diode, by the way. It's a unidirectional flow of electricity. So the whole idea of forward progress for schema migrations is that it's tied one-to-one with your application code, in that your app code is tied to a specific version of the database, and both of them only flow together in one direction. So you're not going to have a time where like I'm going to go back in time for my app code, and I'm going to go back in time for my DB code or something and try and mishmash them. At any given point in time, the two just move together, and it's always forward. And one other cool thing you can do with Postgres, this works with small databases locally, which is what the intention for using it is. Postgres lets you actually clone entire databases just by saying create database template. Like you can just give it any database as a template. By default, when you create a new database, it uses like a database called template1 as the basis for what you're creating. But you can give it anything else. So what you can do is if you have a database, you can say create database app backup, template app. So I basically just backed up my entire database, and Postgres will just copy all the files for that database. And it's actually pretty fast. I mean, even with like a couple hundred megs or whatever it is of like sample data or something locally, it's a very, very fast operation. And then you can do your migrations, and then if it doesn't work, you just drop the database and create it again from the backup. My usual flow for doing any kind of like testing for database migrations, like during active development, is exactly this. I'll create a backup, I'll create migrations for it, and just repeatedly run the migrations, drop the database, run the migrations, drop the database, over and over again, because you get back to the exact same starting point over and over again. And it's very fast. So you can't do this if you have like a terabyte database or something. Obviously, you're not going to do this. But if you're working locally, like your local copy in a VM or in Docker or something, which presumably is not the entire data set, it works very well. So when you actually are making changes to your database, you want to obviously minimize downtime as much as possible. The first time I did, substantial modifications like to migrating a schema on a live system, this picture kind of summarizes what it felt like. You have this car and you want to change the tires, but you don't want to really stop the car. So you have this crazy idea where you can drive on like 2 wheels and hopefully change the tires without dying. That's kind of what it feels like the bigger the migration is. So the general advice for things is the smaller things are, the easier it's going to be and the less likely you are to break something. And the less likely you are to have just issues with things that are going to slow down what you're doing. So like the biggest issue when you're doing any kind of migration is downtime from locks. So depending on the operation you're doing, you're going to have different amounts of downtime. And that downtime can go anywhere from like nothing to a little bit of time to do like some short operation to a very long time for the entire operation. So these three categories I have here with zero in quotes in particular is because there's no real zero. There's always some like minute thing, like it has to update catalogs, things like that. But it's effectively zero for the purposes of any real application. And that covers a lot of stuff. Basically, anything new you do inside Postgres is not going to have any locking impact on existing things. You can create new tables, types, you can add data to them. You might have some performance like degradation just from the system itself being active, but it's not going to slow anything down. Just completely from like locks. Now, then there's some things which have what we call short locks. So this is like creating index concurrently. So this allows you to create an index on a live system without actually stopping the system, and Postgres will do a whole bunch of bookkeeping to make sure it stays in sync. Adding a column if it doesn't have a default value, dropping a column, all these things are instantaneous. So they have a lock, but the lock is like a momentary lock on the system. So when you're planning your schema migrations, you have to make sure that if you don't want your system to actually hang up until the whole thing's completed, you try to keep them within the realm of these things. Now, the things which actually have long locks, which require a lock for the entire operation, is anything like traditional create index, modifying a view, and adding a constraint or adding a column that has like a value that needs to be written to disk. Because each of these operations, the view one's kind of special because you have to lock the view, so it depends on how long the access is going on. But the rest of them involve locking the table because no modification to the table can happen until all of the data for the table has been either read or rewritten. So that's what you want to avoid. And the way you avoid it is by kind of breaking things into smaller pieces and incrementally getting to where you need to be for the end state of your migration. Now, in a traditional application, you have three kinds of data access patterns. It's either something very small and consistent. So you have, I'm looking up a specific user. It's going to be a B tree lookup. I'm going to have probably 3 or 4 I/O operations to get it to scan through. Then you can have something that's known, but it's small. So if you look at like GitHub, for example, if I'm looking at the set of recent PRs, it's only going to be like 10 rows because I'm putting like 1 page worth of data. So I know what's involved in doing this. It's more data than a single lookup, but it's a known small amount. The known and big categories where you have something like I want to export all my PRs or all the commits from this thing or from this repo. And in that case, it's it could be a large amount of data, but you still know what's involved in doing it, and it might actually have like a defined access pattern. That last category, unknown, is when you just let people access your database. So if you have like a bunch of people writing reports or what they claim to be reports against your database, you have no clue what they're doing. There's no way you're going to stop them from doing something stupid. So you kind of, it's not that you ignore that category, but you kind of like, at best you try to silo that category by just having a completely separate replicated system, let people break that system. So when you're designing schemas, the total unknown of anyone doing anything is not even worth thinking about because you're not going to be able to cover every use case anyway. So indexes are kind of how you make things fast, right? So your example in the beginning, we're saying we had like 1 billion rows. If someone has access to that table, yes, in theory they could query everything. In practice, they're not going to scan through the entire thing to find 1 row. We create indexes. Indexes are a bunch of redundant data. They have, there's a cost, like a performance cost associated with it because nothing is free in life. The more indexes you have, the more Postgres has to maintain. But the important thing is Postgres does it for you. Like, so that's the whole point of like indexes, that you don't have to think about it. You're not manually keeping data in sync. Like, here's my fast lookup system. You just create the index, and Postgres does a whole bunch of magic to keep it consistent. And consistency is always priority number 1 because you want things to be consistent. So normally, if you just say create index, it creates what's called a B tree index. This is it's like a fat tree with lots of nodes on each level. And these kind of indexes support things like equals, things like greater than. They support locking. And they also support uniqueness. So you can have a B tree enforced uniqueness on a system, and you say create unique index, it creates a unique index. And again, Postgres, if you do this, it guarantees you're not going to be able to insert 2 things. So I have this invariant defined for my table saying I can always assume there's only 1 of this thing inside the table. Postgres also lets you define what's called partial indexes. So these indexes are on some subset of the data. So rather than indexing the entirety of the table, I can say, I only care about this active set. I might have 1 billion rows, but only like 1,000 of them are active. I want to have an index just on this active set to be able to, to quickly look up things. I only want to maintain that set. So since this index could be so much smaller, it's going to end up being much faster because I might be able to have the whole thing buffered in memory, just depending on the size of what how much of the data I'm actually indexing. There's also a kind of reverse concept where you can tell Postgres, instead of just including these specific fields in the index, I can include other extra data in the index. So normally when you have like a B-tree index, only the fields inside the B-tree index are available to be read in an index scan. What an include statement does when create index is it tells Postgres, oh, I also want to put these other fields in there. So when I look up this value with this index, I also want to be able to get B and C. So I don't have to go back to the table. Otherwise, you have another I/O going back to the table to read them. Now, there's another kind of index, which is my favorite kind, is our expression indexes. So we saw one of these before when I had that example with the lower. So this is really just any immutable expression based upon some row inside the table. So in this example, I'm creating an index on the lower of name. And again, Postgres will just maintain this for me. So I have, it will physically store that lower there, and I can query against it without having to, on the lower of whatever my input is, which is very convenient. So that way you can have one representation of the data itself, like the official representation inside your schema, but then have other ways of querying it without having to maintain those other ways. Because Postgres will just maintain this index for me and guarantee its consistency with the underlying table. Where this starts getting really interesting is you combine all these things together. So you can have an index which is unique. It's on an expression, so on the lower of that name. So I'm saying that lower of that name has to be unique, but only among the active set. So this is when you start defining more like higher level invariants about your schema. And it's things like this that make it, much easier to maintain consistency across your data. Because you can see that even like describing something like this, which normally if you don't have access to each of these individual features and combining together, is not only difficult to do, you have no choice but to do it but in the application. Because these are separate, like I'm maintaining separate things over here of this status versus this uniqueness versus this transformation of the data. And with Postgres, it's very easy to just combine them together by literally just slapping the clauses together. You can even put include afterwards to add additional data if this is the way it's going. The one thing with include is compared to a lot of the other ones is that you kind of have to know what you're doing with your data to be able to add those include clauses, because you need to know what the access patterns are versus just something you're searching for. So views are a pretty common thing people define inside of their schemas. I personally don't use them directly in application code, but they're pleasant to use if you're doing ad hoc querying. I'm sure everybody's familiar with them here. You create views, you give it some fields, maybe you add some stuff in there, you rename, you join some stuff. You can also do some more complicated things like adding in, using set returning functions to kind of just make up data or like make up virtual data. So in this case, I'm generating a series of data of 30 days and getting the most recent 30 days of sales, and it kind of hides away the details of how that's done. So it's all like hidden away inside of the view. Postgres has something else which is even more powerful than this, and that's using set returning functions directly. So in this previous example, you see the view, anyone interacting with this view, if they're filtering something, it has to be one of the fields that's actually there. So that ID, sale date, sale price, quantity, those are the only things I can interact with on this view. A set returning function doesn't have that limitation. So in this case, I have person ID here as a parameter inside of this set returning function called accessible product. And what this does is this is giving me back the set of products that this person is allowed to access. And the way I determine access is that person the owner of the product, or does there exist a product group where that person is a member of a group that intersects with the product group? So what's special about this is that parameter that you're seeing here. When you query this, you say select star from accessible product of whatever the ID is going to be, of the person ID. It allows Postgres to embed that down into the details of the into the inside of the query without requiring the person on the outside to have any understanding of how it works. The only interaction someone on the outside would have, like an end user, let's say writing a report or something on this, is they would just say select star from accessible product, and to them it just works. Like Postgres will figure out how to optimize it. And even better, by default, the way that this works is it will take what you're doing with this, since it's a SQL function, and embed it in the command that the person is running and allow like other filters that are happening to be optimized together. So if I further optimize this product by some other field, if they filter like the where clause of selecting from accessible product, the Postgres optimizer will combine that all together to figure out how to actually query this field. So this is, I like to think of set returning functions as like, it's a strict superset of views, because you can do anything a view can do and a whole bunch of stuff that views can't. So this last thing I'm going to get into is one of my probably favorite examples of things that are normally very difficult until you have the right tools, and they become just like amazingly easy. So this is called the hotel room problem. So normally in a hotel room, like if you go to most hotels, they only let one guest stay in a room at a time. And when people are booking a room, you don't want the hotel to double book your room. If I booked January 1, 2, 3, I don't want someone else to have that same room at the same time. So in a normal, let's say, not so smart database that doesn't have a lot of the cool features that Postgres does, if you're trying to design a system that's going to handle this, you would have a start and end date for your reservation, let's say, and maybe we put a check in place to say that the start always has to be less than the end, because otherwise it wouldn't make any sense. And we're going to make it unique to say that the start date should always be unique. The room ID and the start date should be unique. But that still doesn't guarantee everything, because I could have start today, like on one room, goes for for the next 5 days, and then someone else could have a row for the next day. So it doesn't quite work. But then I could say, okay, maybe I can serialize by doing a select for update on the room ID, and I just won't let people insert anything in, and I'll make sure I do it one at a time, and I'm going to check to make sure, does this overlap, things like that. But the problem there is if I'm doing any kind of check like that, I have to make sure that I do it everywhere. So if I have more than one system, like, oh, we had the old version of the code or this new app or this other thing doing it, I can't really guarantee it's going to happen. I mean, I can guarantee it if you can really say no one else is going to interact with this database, this is the only code that's going to touch it. But you don't know. And you also, stronger than that, is you don't know if your code's actually correct. Because, I might have this one application, it's the only gatekeeper, the only way to book a hotel reservation, but it has a bug. It actually does let you double book the rooms if you do this, weird series of things. With Postgres, you can totally avoid this problem, and it's actually really, really easy. So Postgres has what's called range types, which are range types combined like a normal data type, like an integer or a date or a timestamp. They combine two of them together to dictate a range. So you can say like 1 to 5 or 5 to 10, or like January 1st, 2021 to January 31st, 2021. And they also have a concept of like open and closed. If you're familiar with intervals, there's like open intervals and closed intervals dictating whether the ends of the bounds are included. So what we define here is we have a room ID, which is like the room number, and then you have the booking dates, which is defined as a date range. And the first constraint you're seeing there, the unique key on room ID and booking dates, is saying that create a gist index and exclude any rooms where the room ID matches and the booking dates overlap. So that ampersand operator for range types is the overlap operator. So that will be, if I have two ranges, and by overlap means that there's some set of values which is included in both of those ranges. So here I'm telling Postgres, I do not make sure to exclude any rows where the room ID is the same and the booking dates overlap. And that is literally all you have to do to solve the hotel room problem in Postgres. The other thing at the bottom there is tightening up the ranges themselves, because by default, you can have open, closed ranges. So you want to tighten it a little further to make sure that my ranges are closed in the front and open on the back. But the kind of the meat of this is just having the exclusion constraint there, because it just handles everything for you, and it works marvelously. And again, the whole point of all this stuff is that it's not that you can't do this other ways. It's that by doing this directly in the database itself, in the schema design, you make sure it happens no matter who's interacting with these systems. Because at the end of the day, the consistency is always the most important thing in any kind of data system. So kind of just like summing things up, if you have, if you're designing a schema well and it actually does the things you want to do, it helps you build things really fast. And the reason it helps you build fast is because you stop thinking about breaking things in weird ways. So like in that hotel room example, by having it defined in the actual, in the definition, the invariance for the system itself, that you cannot do this thing, it's not that I'm not going to I'm going to let people do it from the UI, but I'm not going to worry about it happening. I don't have to have this backfill system afterwards to go revert these changes if someone books a room that doesn't happen. And on the other side of it, by using these specific features for limiting the size of the data, limiting what's going in there, limiting the size of my indexes, everything, there's less data is smaller data fits more in memory, and your applications become faster. So Postgres, hands down, is my most favorite tool, favorite system to use to design schemas. So that's my talk. Anybody have any questions? Going once, going twice. Whoop. Oh man. So the question is, what's missing to make the schemas more powerful? That's a really good question. There's always things you wish you could do. If I had to pick one, it would be that if you have a set of tables with foreign keys between them, and you have a parent, and you have two different child tables, let's say. So I have some parent table and foo and bar, both of which are children of that parent. Being able to ensure that the children are also, if they're going to be related through a third relationship, to ensure that they actually are, that they share the same parent. If I did this on paper, this would be a lot easier to explain. But basically, if you go down, if these two people are both children of the same relationship, being able to have a foreign key that says that something else also has to be from the same place without duplicating all the fields everywhere. Because you can do this if you duplicate the parent ID everywhere going down, but you don't want to do that either because it's redundant information. So it's so that's something I wish that Postgres would support. I have no clue if that will ever come in though. Anything else?
So would you recommend keeping business logic in the database or maybe the application, or where is the middle ground where you want to keep business logic on?
Sure. So the question is, do you recommend keeping business logic in the database or or in the application level, and where's the middle ground between the two? At the lowest level, I think all invariants for the system itself, like the check constraints, the relationships, have to be defined at the database level. I mean, it's not even that I don't trust other people to write code. I don't trust myself to write code that can do things that can break. So that's the lowest level. As far as business logic for interacting with that, it depends on what it is. A lot of the times it is easier to do things in the application level just because the ordering of the things you want to do, if there's a hierarchical relationship of foreign keys, the ordering is sometimes easier on insertion to do on the application side, but the reverse is true on the deletion. So like having cascading deletes, things like that, it solves on the way out. So there's not one answer on the modification part of it, but as far as like enforcing the constraints, that always has to be at the database, because that's the only place where it's it's the last place to stop it before it becomes permanent record. Anything else? All right. Thank you.